Let's keep practicing using our limit laws to find limits. Again, the point here is to take functions that would be kind of a hassle to plug in values. Making a table would be a huge hassle. So we can use these laws to speed up this process and avoid having to make tables and get precise limits, not estimates like a table does. So here, if we look at this function, we want to find the limit as t approaches 1 of t plus 6 over 2t to the 4th power. Okay, so if we look inside of that, we can see that our function is actually a quotient. It's a ratio of two separate functions. Well, our limit law about quotients, the quotient law, says that the limit of a quotient is equal to the quotient of the limits. So I could split this up and say this is the limit of t plus 6 over the limit of 2t to the 4th power. Right? Well, now I could break this down a little bit further here. In the numerator, this is the limit of a sum. It's t plus 6, and we saw that the limit of a sum is equal to the sum of the limits. We also saw in the bottom here we have a constant times a power, and we saw that we can move the constant out front on the constant multiple rule. So we could write this as 2 times the limit as t approaches 1 of t to the 4th power. But we also saw that when we have a power inside of our function, we can just evaluate the limit of the base and then raise the limit, the whole limit, to that power. Right? So that was our power rule from our constant laws up top. So we use, again, the point here is we use the limit laws to break the complicated function into lots of little pieces that give us very, very simple limits that we can evaluate using the two basic rules that we learned in section 2. That the limit of the identity function is whatever value you're heading toward, and that the limit of a constant is that constant value. So here we can evaluate all these limits here. The limit as t approaches 1 of t, that is to say, as t goes toward 1, what does t go toward? Well, that means t goes toward 1. So this would be 1. The limit as t approaches 1 of t is 1. Excuse me. Next, the limit as t approaches 1 of 6. We have a constant function here. So as t goes toward 1, 6 is constant, it stays the same, it's always the same value. So we'd have 6 as our limit, right? The limit as t goes toward 1 is 6. In the bottom, we have the limit as t goes toward 1 of t. We already saw up here. We know that that's 1. So this would be 1. But we know it's getting raised to the 4th power and being multiplied by 2. So that gives us 7. 1 to the 4th power is 1 times 2 is 2. So we have 7 halves is our limit. The limit of t plus 6 over 2t to the 4th power as t goes toward 1 is 7 halves. Let's do one more. Okay, another kind of ugly looking function. It would be not very fun to have to plug in a lot of decimal values into this and make a table, so we'll split it up using our limit laws. We can split this up and we have a product right here of t to the negative 1/4 power times t plus 5 to the 1/3 power. So we can split it as a product first. We'd have the limit as t approaches 3 of t to the negative 1/4 power. And that would be multiplied by the limit of the other factor, the limit as t goes towards 0 of t plus 5 to the 1/3 power. And then we can break this apart even more here. We can move this power outside of the limit, right? The limit of t to some power is equal to the limit of t to that power, right? We can take the limit first and then evaluate the power. Over here, we have this 1/3 power on the t plus 5, so we could take t plus 5 and raise that whole limit to the 1/3 power. So in both of these factors here, we move the power to the outside of the limit. Inside of this one, we have one more step that we could do. So we'd have the limit as t approaches 3 of t raised to the negative 1/4 power times here we have, this is a little bit tricky here, but we have the limit of a sum, so inside of these square brackets we can split that up into two limits, right? Because the limit of a sum is equal to the sum of the limits. And then that sum would be raised to the 1/3 power. And again, notice we're down to only the limit of t and the limit of a constant. These two basic limit rules that we learned in section 2. So the limit as t approaches 3 of t is 3, and that's raised to the negative 1/4 power. And on the right, we have the limit as t approaches 3 of t, which again is 3, plus the limit as t approaches 3 of 5, which is 5. And then that is all raised together to the 1/3 power. So if we're just doing some basic arithmetic here, a negative exponent causes the base to move into the denominator. The 1/4 power, that's the first power in the fourth root, so we could just call this the fourth root of 3. But make sure the negative moves the base into the denominator. Then we also have 3 plus 5 here is 8. 8 raised to the 1/3 power. 1/3 power really means the third root. So this would be the third root of 8, which is 2, divided by the fourth root of 3. If you were really worried about it, you could rationalize that denominator. I'm not going to bother right now. That's not what we're focused on. So this would have been a very difficult problem, very difficult limit to find by making a table. First of all, it would have been super tedious to plug in 1.9 into this, and 2.9 and 2.99 and 2.999. It would have been a huge hassle to plug in all those values. Secondly, when you did that, you would have been getting a bunch of crazy irrational decimals, because this is an irrational value, right? The cube root of 4 is some fraction less than 1. 2 divided by that might be 2.735 or 62917, right? It's going to be some crazy irrational, and it'll be very, very difficult to actually discern what that function value is heading toward when you look at the table of values. So this is very much advantageous over making a table in multiple ways. It's faster, it's more precise, it gives you a specific limit, and it gives you an exact value. And it's not an estimate. Like we said, the table of values is just an estimate based on what it looks like it's going toward. So the last thing I'll say about these limit laws here in this last video is some of you certainly are noticing that kind of essentially what happens here is as you break the function apart, you end up you're just plugging the limiting value into t and evaluating all of the commands from the function anyway, right? If I had just started up here and said, well, let me just plug 3 in for t and say 3 to the negative 1/4 times 3 plus 5 to the 1/3, and I would immediately go right down to that step. And you're probably looking at that saying, well, why do we have to do all this convoluted law of writing all these things out and writing 100 limits instead of just plugging it in? Well, that's really what we're going to focus on in the next section is, well, does it always work that way? Can I always just plug the number that I'm heading toward into the function and get the limit that way? Or are there exceptions to that, and so on? So in the next section 4, we're going to focus on when and why can I just plug the value in? Because the answer is most of the time yes, but a lot of the time no. So we have to be really careful and make sure we're not just plugging it in right away. But we'll focus on that in the next video, or in the next section. But for this section, on the practice, you'll just be practicing splitting complicated functions up into smaller and simpler pieces so that you can evaluate the limits exactly without having to make a table of value. That is exactly what you'll be doing here in this homework assignment right here. Enjoy.